Welcome back to the Real Number System. In section 6.1, we're going to begin talking about rational numbers. So we'll look at different models for rational numbers. We'll talk about equivalent fractions, and we'll talk about simplifying fractions. We'll talk about ordering our rational numbers, and then we'll talk about the denseness property of rational numbers. So let's get started. What is a rational number? Now, Q is the letter that is frequently used to represent our rational numbers. And you'll notice here, Q is the set of all A over B, such that A and B are integers, and B is not equal to 0. What this means is the set of rational numbers is the set of numbers that can be written as fractions. So we're looking at fractions. We're looking at what we call terminating decimals, decimals that stop, and also repeating decimals. The top of a fraction is called the numerator, and the bottom is called the denominator. There are several ways we can write fractions as A over B. We could also write them as A/B or A divided by B. A proper fraction is when the numerator is smaller than the denominator. So 4/7 would be a proper fraction. Now, one thing that's left off of this definition is what if you have a negative? So negative 4/7 would also be a proper fraction. With our proper fractions, if we have a negative, such as negative 4/7, that is a proper fraction because the absolute value of that numerator, the absolute value of negative 4, is less than the denominator. So with an improper fraction, the numerator is greater than the denominator. 7/4 and 6/6 are both improper fractions. Now 6/6 is improper because the definition is not just greater than, but greater than or equal to. And again, if I have negative numbers like negative 7/4 or negative 6/6, these are also improper fractions. What this definition leaves out is the absolute value of the numerator is greater than the denominator. When we're thinking about fractions, there are several things that we have to understand. First, we have to think about what our whole is. Second, the denominator of the fraction tells us how many equal-sized parts that whole is divided into. It's very important that the whole is divided into equal parts. And then third, the numerator of the fraction tells us how many parts are selected. Again, that whole is very important. So if I think about 1/4 of a dollar, the dollar is my whole, and 1/4 of the dollar is 25 cents. However, if I think about 1/4 of an hour, the hour or 60 minutes being my whole, 1/4 of that is 15 minutes. So we have to pay attention to the context. We need to think about what our whole is in every case when we have a fraction. Now, let's look at some specific models that we have for fractions. One model is the area model. Notice here, this diagram represents 1/3. It represents 1/3 because the whole is divided into 3 parts. And notice that one part is shaded. Now specifically, when I think about the 3 parts, I think about 3 equal parts. A second model that we can use to represent fractions is our number line model. Every number can occupy only one spot on our number line. On this number line, we have shaded 2/3 because our whole is divided into 3 equal parts. And notice that 2 parts are shaded. So I could count on the number line 1/3 and 2/3. The set model is another model that we use for fractions. The whole is the number of elements in the set, and the part is the number of items that are shaded or the number of items that we are selecting. Notice here that our model represents 3/5. Our set has 5 elements, and 3 of these elements are shaded. A final model that we'll look at is fraction strips, or sometimes called fraction tiles, or you may see them as fraction circles. Notice we have a strip that's red that represents our whole. Below that is pink. Notice that the whole is divided into two parts, and one pink is one of those two parts, or one half. Then we have green strips below that. Notice that the whole is divided into 6 parts here, and each green strip represents one of those 6 parts. Equivalent fractions are numbers that represent the same rational number. Notice here that our rectangles are the same size in each figure. The shaded part is also the same size. But in the first figure, the whole is divided into 3 parts and 1 part is shaded. In the second figure, the whole is divided into 6 parts and 2 are shaded. And the last figure has 12 equal parts with 4 of those shaded. But again, notice that the shaded part is the same size in each rectangle. This tells us that 1/3 is equivalent to 2/6 is equivalent to 4/12. The fundamental law of fractions tells us that if we multiply the numerator and the denominator by the same whole number, we get an equivalent fraction. Now this helps us with our negative fractions. So 7 over negative 15 is the same as negative 7 over 15. Now we really prefer negative 7 over 15. We don't want to have that negative on the bottom. Now here's why these two fractions are equivalent. So 7 over negative 15, if I multiply the top and the bottom both by negative 1, 7 times negative 1 is negative 7, and negative 15 times negative 1 is positive 15. Again, when we're working with fractions, we prefer to write the answer with a negative on the top, negative 7 over 15, and negative out front, so negative 7 over 15. We typically do not want to have that negative written in the denominator. Let's find a value for x that will make our equation true. I want to think about the number that I need to multiply the numerator and the denominator by to get that fraction on the right side. So 42 goes into 210 5 times. To make that equivalent fraction, we have multiplied the denominator by 5. 42 times 5 is 210 on the right side. If I multiply the denominator by 5, by the fundamental law of fractions, I also have to multiply the numerator by 5. And 12 times 5 is 60. And so x, in this case, is 60. Let's look at another example. 2 over 3 equals 16 over x, and I want to know what x is. So I want to think, what number have I multiplied the numerator and the denominator by to get the fraction on the right side? Well, 2 goes into 16 8 times. So here I've multiplied the numerator by 8. 2 times 8 makes 16. If I multiply the numerator by 8, by the fundamental law of fractions, I also have to multiply the denominator by 8. And 3 times 8 is 24. In our next video, we'll pick up with simplifying fractions.